Yes.
I had registered for one class for next semester, and they asking, can you send like a letter again, like you did last semester or this semester, and saying that I only take this one class for like to be a full time student.
Okay. Um, okay. Okay. I don't remember. I mean, I remember the instance, but I don't remember what they needed to hear from me. Um, I'll see if I can find it on my files. I think I probably can. Did they give you any specific information I needed to include in the letter? Is there any?
Just saying, oh, just saying that this is the only class I can take for this semester,
Okay.
so I can be a full time student.
Okay. Okay. I'll try to remember to do that. There's so much going on right now. I can't tell you when I'll do it. Um, I have to go back to the clinic today to get typed for the blood transfusion. But I think I'll have some time after this class and before I need to leave that maybe I can find that letter and send it again. Do I have to tell them which class it is? That's what I'm asking. Do I have to tell them, or just that you?
I don't think you do.
Okay. What class is it? Do you know?
Physics 200.
No, we don't have a physics 200. We have a physics 201 and
Oh,
202.
201.
201. Okay, okay. Physics 201. Okay. Um, and you're through with all your other classes. That's the only one uh, you need. Are you going to take 202 in the summer?
No, sir, I'll be done after this one.
Okay, okay, okay. So that's the only class you can take and need to take. So you need to be able to get counted that as a full-time student. Okay. All right. I'll try to get that done unless something else comes up. And today, this has been such a crazy day. I can't guarantee nothing else is going to happen, but I'll try to get that done between classes today. And who do I send it to? The registrar's office, financial aid office, business office? Who does it go to?
Like the rest of the office.
Registrars? Okay.
Yes, sir.
Okay. I'll try to find the other one, so I'll make it as close to that as I can. That less I have to do, I just change the dates and things like this. But if I can't find that, then I'll send something to registrar's office, and I'll tell them if somebody else needs it, please forward it to them as well. Okay.
All right, thank you.
All right. Glad to. All right. Anything else? We are recording now. So where we left off last time, we're in Chapter 4, Higher Order Differential Equations, in Section 4.3, Homogeneous Linear Equations with Constant Coefficients. Okay? Now, we just finished the example 4, and that illustrated a special case when the auxiliary equation has repeated complex roots. And remember, we did that one last time. And I thought I would go straight to this, but I think I'll go back to the book here so you'll see it. Okay. Now, I'm going to scoot y'all down a little bit because I can't get to my arrow. Okay. Here was the situation we had last time, example 4. Okay. When we did the auxiliary equation, we had m4 plus 2m squared plus 1 equals 0. Okay. And when we did the roots, I can't see them here, so I'm going to have to move y'all again up here. Okay. It has roots. M1 and M3 were both i's. Okay. M2 and M4 were minus i's. Okay. So this was a combination of case 3 and case 4. Case 3 was the circumstance that you had imaginary roots, which you have 2 of here. And case 2 was the fact that you had repeated roots. So we had repeated imaginary roots. Okay. Now, The imaginary roots required us to have, by Euler's formula and working through that, we came up with cosine plus sine, okay? And the reason there's no e to the alpha, there was no real part of either one of these roots. They're both only imaginary. If that had been 1 plus I and 1 minus I, then we would have had an e to the x in front. We didn't have that. So there is no e to the x part of it. And the beta part, that's the imaginary part, that's 1. So that's why it's cosine x and sine x. C1 cosine x, C2 sine x. Okay? Now, then the second part, the repeated part, that then came upon, what you can do with that is put an x in front of both of those and new coefficients, C3x cosine x and C4x sine x. Okay, so that represented a special case in which the auxiliary equation has repeated complex roots. Before it was repeated roots or complex roots or unique roots. Okay, those were cases 1, 2, and 3 in some order there. Now we had a mixture of repeated roots and complex roots. Repeated roots had the factor of x added to it. The complex roots meant you were in sines and cosines rather than e to the alpha mx. Okay, now that's where we pick up here. So example 4 illustrated the special case in which the auxiliary equation has repeated roots and complex roots. In general, if M1 was alpha plus I beta, now that one we had in example 4 was only the I beta part. It was just I and minus I, okay? If beta is greater than 0, okay, and it always, I think, will be greater than 0, is a complex root of multiplicity k of the auxiliary equation with real coefficients, then the conjugate M2 alpha minus I beta, so that's why they said beta positive here, so this would be a minus I beta, also is a root of multiplicity k. Remember, your complex roots always go in conjugate pairs. Even when they're repeated, they'll be repeated in conjugate pairs. Okay? So, from that, if there are 2k complex valued solutions, okay, e to the alpha plus I beta x. Now this is in the old thing before we do the Euler formula, okay? If that's what it came up with, then you're going to have an e to the alpha minus I beta x. And if you had k of those, then you have an x e to the I alpha plus I beta x, e to the x times e to the alpha minus I beta x. You have an x squared in front. You have an x cubed in front, up until you get to x to the k minus 1 e to the alpha plus I beta x. Okay. In other words, you'll have the basic and then ones with x in front, x squared in front, x cubed in front, up until, if you had multiplicity of k, you go up until you get to k minus 1. Don't go as far as k, but k minus 1. Okay? Now, what this produces, the alpha produces the e to the alpha x. And that just gets repeated in every one of them. Okay? There and there and there and there. Every one of them has that e to the alpha x. And that's all you do. There's no special coefficient that you have to deal with that. It's e to the alpha x. Okay? Then the I beta x, e to the I beta x, and e to the minus I beta x, they result in cosine beta x and sine beta x. So since this one has an x in front, it'll be x times e to the alpha x cosine beta x, and then e to the alpha x e to the alpha x sine beta x e to x squared e to the alpha beta. Okay, so you just keep adding your x's in front until you get to k minus 1, x to the k minus 1, but the rest of them are exactly the same. Now, in example 4, that one we just did, we identify k is equal to 2 because you had multiplicity of 2. Your alpha was 0, so you didn't have the e to the alpha x there. That was just 1. The beta was 1 because it was plus or minus I plus or minus I. Okay, so the beta was 1. The I coefficient was 1. Now, what if we have rational roots? Okay, of course, the most difficult aspect of solving constant coefficient differential equation is finding those roots of the auxiliary equation. Now you have to go back to the day when you were in pre-calculus algebra and you did your you found your zeros of polynomial functions. That's exactly what you're talking about here, finding the roots of polynomial functions, because those auxiliary functions are polynomial functions, especially when those are degree greater than 2. If they're degree 2, you either factor or use the quadratic formula. That's it. Okay? If you degree greater than 2, you got work on your hands. Okay? Sometimes we can try to test the auxiliary equation for rational roots, and that's what we're going to talk about next. Recall from pre-calculus mathematics that if M1 is some ratio of P over Q, a rational root, that's what it means, a ratio of two integers, expressed in lowest terms, that's important too, of the polynomial equation. And the polynomial equation, now they're writing in the right order, a sub n x to the n, m to the n plus a sub n minus 1 times x to the nth minus 1 power, and all the way down to a sub 3 times x cubed, m cubed plus a squared times a sub 2 times m squared plus a sub 1 times m plus a sub 0 is equal to 0. That's your polynomial equation. Okay, if it has integral coefficients, all these a's are integers, and remember, they will be in these cases. Okay, that's a requirement that the c's all be not the c's, the coefficients are no, I'm sorry, they're just constant coefficients. Okay, but real coefficients. Okay, but if these are all integers, then the p, the numerator of that first attempt here, is going to be a factor of your constant term a sub 0. The q, the denominator of that, is going to be a factor of the leading coefficient a sub n. Now remember, the requirement here, the a sub n cannot be 0, so therefore the q will never be a 0. All right, now hopefully this will ring bells when we do it. Okay, so I'm going to go to the whiteboard, which means I'm going to have to move y'all around a little bit again, but that's okay. Y'all are not heavy, I can move you easily. So I'm going to scoot you down over here. Okay. This is example 5. Okay. If I can get the pen to show up, there it is. 3y triple prime, that's the third derivative of y with respect to x, plus 5y prime, y double prime, if the pen would write, okay, plus 10y prime minus 4y is equal to 0. Now, there's your problem. Now, I do a little bit more than the book does, just so I remind myself of what's going on. Here we have a third order linear differential equation with constant coefficients. Now these constant coefficients happen also to be integers. Okay? Now, even with the constant coefficient, the assumption of a solution is y is equal to e to the mx. That's where we always begin when you have constant coefficients of a linear higher order differential equation. Y is equal to e to the mx. Now I'm not going to go through all the details here, but I will do this. This then would result in, when you plug that in, and the e to the mx is never 0, and this whole thing is going to be equal to 0, then you know that you have 3m cubed plus 5m squared plus 10m minus 4 equals 0. Now, if you haven't figured out that's going to happen every time, that is going to happen every time. Now, usually when I have a situation like this, the first thing I look for to see if factor by grouping will work, because you have an even number of factors, you're not missing any terms. There's a 3, 2, 1, 0 blast off for your your exponents there. You're not missing any terms, even number of terms. See if factoring by grouping will work. Group the first two together, last two together, no way. There's no common factors there. Always check that out first. That's an easy thing to check. Okay, so the next thing is use your rational zeros test. That's what you used to call it in pre-calculus algebra. You're looking for a ratio P over Q where P is any factors of your constant at the end. And what are your possible factors there? Plus or minus 1, plus or minus 2, and plus or minus 3. Those are the only factors of 4. If I said 3, I meant to say 4. Okay? Your Q is all the possible factors of your leading coefficient. And that's always plus or minus 1 and plus or minus 3. That's the only factorization of 3. Okay? Now, back in pre-calculus algebra, they like for you to list these in ascending order of value. Okay? I didn't like to do that. I like to do my integers first and then the fractions later, just because I like integers better than I like fractions. So here are your possible coefficients. Okay? I mean, not coefficients, rational roots. You got plus or minus 1, plus or minus 2, and plus or minus 4. That's these three numerators over the plus or minus 1. Okay? So then let's do these three numerators over the plus or minus 3. So that would give you, this is so aggravating. Okay. That would give you plus or minus 1/3, plus or minus 2/3. That's a 3. It's an ugly 3. And plus or minus 4/3. Okay. Now, I know that's hard to read, but hopefully you're writing it down much neater than I am. Okay. Now, the easiest one in the world to do is plus or minus 1. Or it's plus 1. Just plus 1. Now, what does plus 1 give you? If you put m equal plus 1, you get 3 plus 5 plus 10 minus 4 equals 0. Is that true? Can't possibly equal to 0. So plus 1 is out because you got 18 plus and minus 4, never going to be 0. So plus 1 is out of there. So I'm going to take my eraser, if I can find it. In the first class it wouldn't erase, or my middle class it wouldn't erase. First class it did fine. Okay, so that one's out of there. Plus 1 is out. Okay. Oops. So I think I'm going to come over here and wipe out the plus 1. Now, in my mind, minus 1 is pretty easy too. Now, you could plug it in like I did for 1, but that was so easy to do. I think I'll do synthetic division. So do minus 1 on the outside, and then do your coefficients on the inside. 3, 5, 10, and minus 4. Now I did leave something out, and the book didn't mention it, and that's why I forgot about mentioning it. Remember, you have more tools in your belt than the book is indicating. One thing that you have, a very handy tool, is Descartes' rule of signs. Descartes' rule of signs says if you count the sign changes in your function, in your polynomial there, you can know how many positive real roots you have. Well, this is plus to plus, no sign change there. Plus to plus, no sign change there. Plus to minus, there's one sign change. That means you have one possible, in fact, you have to have one rational real root. Okay, well now we're dealing with minus 1, so that's not in the picture. If you had substituted and put a minus m in here, this would be a minus 3m cubed plus m 5m squared, a minus 10m, and that stays a minus 4. That would give you one sign change, two sign changes. So you either have 2 or 0 sign changes that are negative. So that's why we're going to look at the negative. I meant to tell you that before, but I forgot. Now, also, I count the number of numbers I have here. 1, 2, 3, 4. That has to be one more than your largest power. And indeed, that's true. And we're in descending order of the power. 3, where is the pen? 3, 2, 1, 0, blast off. Okay, so everything is set up. Skip a line, draw a line. That's my rule. You'll never read it in a book, I don't think. Bring down the 3. Now you multiply and add. Minus 1 times 3 is minus 3. Add positive 2. Multiply minus 2. Add positive 8. Multiply negative 8. And add negative 12. Now, I would have normally stopped before then because I knew it wasn't going to work. But here's another rule. This is the lower bound test. If you're dividing by a negative number, which we are, okay, negative 1, if these had come up alternating signs, you stop. You are not going to go any more negative than that. You can go less negative, but not more negative. These are not alternating signs. It's plus, 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 minus. So therefore, we can go to negative 2. We can go to negative 4. We can go to negative 4/3. Okay? And we can certainly go less. Okay. So that didn't work. So I'm going back to my eraser if I can get it to work. Okay. Because I have limited room to write. I'm going to change the number outside the house. I don't have to change it inside the house. Okay. And I'll change the numbers everywhere else. Okay. Oops. Keep going to the wrong place to reactivate. Okay, next. Okay, so not only is plus 1 out, minus 1 is out. So both of those are gone. Let's try 2. Let's see if 2 will work. Okay. Again, bring down. I should have left that down there. 3. 2 times 3 is 6. 5 and 6 is 11. 2 times 11 is 22. 10 plus 22 is 32. 2 times 32 is 64. And 64 minus 4 is 60. Time out, folks. Okay. Now, whenever you're dividing a positive number and your quotient line at the end comes out all positive, stop there. You've reached your upper bound. That's the upper bound test. So therefore, not only is 2 out of the picture, plus 2, yuck, this thing is so aggravating. The plus 2 is out of the picture. There, it did it again. Okay, plus 4 is out of the picture because it's greater than 2. This thing drives me nuts. Okay, plus and minus 1 are out, plus 2 is out, plus 4 is out. We don't have anything else greater than 2, so the others are still game. Okay, so between Descartes' rule of signs and your upper and lower bound test, you can eliminate some work. I'm all in favor. Okay, so let's erase again. If I can get the eraser to show up now, we're going to erase the 2, the 6, the 22, the 64. Going to leave the 3 there because that's always going to be there. You bring that down anyway. I forgot that last time. Okay, go back to my draw mode. What's next? Well, negative 2 is still good. So let's try negative 2 and bring down the 3. Negative 2 times 3 is negative 6. 5 minus 6 is minus 1. Minus 2 times minus 1 is positive 2. This will be 12, and this will be minus 24. Okay, that becomes minus 28. Normally I would have stopped before there and said, nope, that's not going to work, but I wanted to point out to you, notice here, plus, minus, you're dividing by a negative number, you're alternating signs. Plus or minus 2 is not going to work, and anything less than minus 2 is not going to work. This is not turning out well, is it? Okay, so we're plus or minus 2 are out, plus or minus 1 are out. Now minus 4 is out because anything less than minus 2 is out, so we didn't even have to do that one. And we've got our fractional forms, boo hiss. Okay, so let's go to them. I'll put those off till the end because I don't like messing with fractions. So let's change our minus 2 and these numbers and this numbers. Okay, go back to our draw mode. Let's try 1/3. Okay, we've already brought down the 3. 1/3 of 3 is 1. 5 and 1 is 6. 1/3 of 6 is 2. 2 and 10 are 12. 1/3 of 12 is 4. Look at that. Ding, ding, ding. We finally hit a winner. Okay. Now, we know that x equal 1/3 is a 0 for that function. M is equal to 1/3. So M equal 1/3 is our winner. Now let's pause for a moment here and think. Okay, longer if it's necessary. Okay, remember Descartes' rule of signs? You can only have one positive real root, rational root. We found it. Don't look any further. Positive 2/3 is out. Positive 4/3 is out. Okay. Okay, this thing is aggravating again. Okay, the positive 4/3 is out. Okay, now, but guess what? We really don't care that much, do we? Because once you get down to 3 numbers in your quotient, those represents a quadratic. So this will be 3m squared plus 6m plus 12 equals 0 is going to be a factor. And guess what? We can factor out a 3. 3 times m squared plus 2m plus 4 is equal to 0. Okay? Now, what you have to ask yourself, is there any value of m can you factor this and get that equal to 0? You know 3 is not going to be equal to 0, so forget about that. Is there any factorization here? And I'll tell you, no, there's not. Since there's no factorization, we go to the quadratic formula. That tells us that m is equal to minus b, that's minus 2, this is your b here, minus b plus or minus the square root of b squared, the b squared, b is 2 again, so that would be 4, minus 4a, a is 1, so that's fine, and c is 4. Okay? Now as soon as we get that, you see there's a problem, and then you did 2 times a is 1, so that's just a 2. Alright. Now, I can already tell it's not going to turn out well. Minus 2 plus or minus the square root of 4. Now, when you get here, you count the number of negative signs. You've only got 1, so that's going to be minus. If you had 2, that would become a plus. If you had 3, it stays a minus. Okay? And that's 4 minus 16. I can tell this isn't turning out well over 2, which means you got a minus 2 plus or minus the square root of negative 12 over 2. Well, that is minus 2 plus or minus. Now I'm going to factor this negative 12 into a minus 1. Well, minus 1 gives you an I. The square root of minus 1 is I, not your vector I, just the imaginary unit I. Also, you have a perfect square of 4 in there. Square root of 4 is 2, so that's going to be 2i. Okay, and then you also have a factor of 3 in there. The square root of 3 is the square root of 3. Well, this is divided by 2, so the 2's go out here, and that gives you m is equal to minus 1 plus or minus I root 3. And I like to write the I in front. Most books, oops, that's not a vector. Okay, I root 3. Okay, I'll just finish the linear algebra. No, oh, hey, here comes Kira back. I didn't know she had left. Okay, sorry about that. And frankly, this is crazy. It may have something to do with my health. I bounce back and forth between being too hot and too cold. So I'm going to have to turn down the thermostat again. I may have to turn it up later, but I'll be right back. Let me go turn it down. I meant to turn off the recording too, but I wasn't going that long. However, I am going to record this. I didn't get to eat much lunch today because of all the telephone calls. I need another bite. I'm running out of energy. I'm so sorry. Rude and impolite to do, but this has been a strange day. Okay, so there is our complex root. Okay, remember we said on the negative side from the Cox rule of signs, you either have 2 or 0 negative real roots. If we had no negative real roots, so they both wound up being complex here. They don't have to be negative, because what is that talking about anyway? So all this put together, what's your solution? Y is your function, is equal to, we know this is one of these, remember, it's y is equal to e to the mx. Your first m was 1/3. So this is C1, there's your arbitrary coefficient, e to the 1/3 x. I'm going to write it as x over 3 because it's easier to write. Okay? Plus C2, well, actually, I'm going to do something else first. The next two roots, because you have third degree polynomial, you're going to have 3 roots, functions, that are linearly independent. We're going to have an e to the minus x in there. That comes from the alpha part here. So let's just go on and write that down. Plus e to the minus x times, now we'll deal with the beta part here. The beta here is square root of 3. So that would be C2 cosine the square root of 3x plus C3 times the sine of square root of 3x. There's your solution. This is so aggravating. Okay, I try to put a little tick mark here and it just doesn't work. Okay, now that's just to show you the x is outside the square root. Okay, there's your solution. 3 for some reason, there it is. 3 arbitrary coefficients, because it's a third degree differential equation. 3 functions here, e to the x over 3, and then this function is a product, e to the minus x times cosine root 3x, and e to the minus x times sine root 3x. I just factored out the e to the minus x there, okay? And then the 2 other arbitrary coefficients go with that. There you have it. Any questions on that? Okay, so that gives us C1 e to the x over 3 plus e to the minus x times C2 cosine square root of 3x plus C3 sine square root of 3x. Got it. Okay. Now, that basically just about wraps up what we're doing right here. So let me clear the drawings. Didn't have to do that. Let's see. Let's go back to the share and share the book again. All right. So there we have solved, finished example 5, and there was the solution we got. Y is equal to C1 e to the x over 3 plus e to the minus x, that came from your the alpha being a minus 1, times C2 cosine square root of 3x. The square root of 3 came from the fact that the beta is the square root of 3 plus C3 sine beta x. Okay. Now the rest of this I don't think is all that crucial or important because they're talking about using computers. And if you have Mathematica or Maple or one of those packages that you have at your disposal, you can play around with this. And that's what they're talking about here. So let's just scroll on down. Now, in the classic text, differential equations by Ralph Palmer Agnew, that's back in 1960, and I'm wondering if maybe that's the one I used. It was a great text, because I came along, I was in college in 69 to 73, so that would have been about 71. I believe it was when I was there, so I could have used that one. The following statement is made. It is not reasonable to expect students in this course to have computing skills or equipment necessary for efficiently solving equations such as blah, blah, blah. Look at those coefficients. Decimal coefficient, really ugly decimal coefficient. Although it is debatable whether computing skills have improved in the intervening years, it's a certainty that technology has. Since 1960, yes, it has. Okay. If one has access to a computer algebra system like Mathematica, Maple, CAS, any of those, then that could be a reasonable equation. After simplification and some relabeling, Mathematica yields this approximate general solution. Okay, it won't be exact, and you'll see no correlation between these numbers and those numbers. Okay, but it will help you solve this. And again, that's technology. Finally, we're faced with an initial value problem consisting of, say, a fourth order differential equation, then to fit the general solution of the differential equation into 4 initial conditions. We must solve the 4 initial linear equations in 4 unknowns, C1, C2, C3, and C4 in the general solution, and using a CAS, that's computer algebra system, to solve that system of equations can save lots of time. And they'll talk about this in later problems. Okay? Now, that's it. No other things. Here's your homework exercises for 4.3. Any of the odds that are in the back of the book of 1 through 13, they're open game. Any of the odds 15 to 27, they're open game. Any of the odds 29 through 35, they're open. If they're in the back of the book, by all means do them. Okay? Then either 37 or 39. Now, is this somebody coming in? I don't think so. I think it's just my cursor flying down there and breaking it come up. Okay? Boy, we only had 3 people out of 8 in my Cal 3 class, and we had now only 2 out of 5 in this class. I don't know what's happening here. Maybe it's because I've been late to both classes. I don't know. So but 41, if that's in the back of the book, go for that. 43 through 47, if those are in the back of the book, go for that one. There's 43, 45, and 47 is up top. Right there. And any of the odds 49 to 57, right there. Usually the discussion problems are not have answers in the back of the book, so don't sweat those unless they happen to have some of them in there. Then it's probably a good idea to take a look at them. Any questions on 4.3? All right. Now we move on to 4.4. Now, what you've done so far is linear differential equations, higher order linear differential equations with constant coefficients, homogeneous type equations. What if you have a non-homogeneous? That right-hand side is not 0, but some function of x. Still have constant coefficients here, but now this is some function of x. Now, here's the 2 things that you have to do. You first have to find the complementary function y sub c. What is that? That's what we used to call your solution to the homogeneous case. You set the g equal to 0, and that gives you your complementary solution, y sub c. That will have your c arbitrary coefficients, because remember, if it's a linear differential equation, you're going to have c, and of nth order, you're going to have n possible solutions to that auxiliary equation, and they will be your complementary solution. Those linear arbitrary coefficients. I'm running all over my cord and I don't know why. Okay. Now, then what you have to do is find any particular solution, y sub p, that solves it for the g of x. So you first do the complementary function that solves it for the homogeneous case where g of x is 0. That gets you all your arbitrary coefficients, but it's not a complete solution. Then you do your y sub p, which is a particular solution that solves for the g of x. Those will not have arbitrary coefficients in them, okay, in general. Okay. Then, as we discussed in 4.1, the general solution will be your complementary solution plus your particular solutions, okay? The complementary solution y of c is the general solution for the associated homogeneous differential equation when the g of x is equal to 0, and then we'll learn how to do the particular solution. That's mostly what we're going to talk about in this section. In 4.3, we saw how to solve the homogeneous equations with constant coefficients. Now we'll be working on the particular solutions when the g of x is not equal to 0. There are two ways for obtaining that particular solution for a non-homogeneous linear differential equation with constant coefficients. It's called the method of undetermined coefficients, okay, and that's what we're going to be working on now. There are two ways to do this. One is called the superposition approach, which is what 4.4 is doing. The other is called annihilation approach, which is what 4.5 covers. Now, I've taught both ways, and in general, it seems like students understand the superposition approach a little bit more easily than they do the annihilation approach. They're basically very, very similar in my mind. I don't see much difference in them, but it just seems like students understand superposition a little bit easier because we've already been doing things with superposition. We haven't been annihilating as much, unless, of course, you're a Arnold Schwarzenegger fan or Schwarzenegger fan. Okay. You may be an annihilator. I don't know. So, I think we've already beat that to death. Okay. The underlying idea behind this method is a conjecture about the form y sub p, that particular solution, which is basically an educated guess, okay, that is motivated by the kinds of functions that can make up this g of x. The general method is limited to linear differential equations such as this, where the coefficients are constants. Of course, that was always the case. All these coefficients had to be a constant. That was the case for the complementary solutions, which is the general solution for your homogeneous case. It's still going to be the case now. So all your A's have to be constants. Okay? Now the g of x, are there any requirements on that? G of x is the thing on the right hand side. Let's see if I can get it to show up here. I don't. Yeah, there it is. That g of x. What has to be true of that? Well, it's either going to be a constant, k, other than 0. If it was 0, you got it done already. Okay? It could be any polynomial function. Any polynomial function. First degree, second degree, 0 degree. Well, 0 degree is a constant k. Any degree of polynomial. It could be an exponential function. e to the alpha x. It could be a sine or a cosine function, sine beta x or cosine beta x. Now, I kind of dislike that they use betas again, but it could be. Or finite sums and products of any of those functions. Constants times polynomials times exponentials times sines times cosines, or it could be sums or products of those functions. Now, what we get to next here is a little note mostly to me, but I've already sort of explained it to you. In this section, the method of undetermined coefficients is developed from the viewpoint of superposition principle for a non-homogeneous equations. Okay? In section 4.5, an entirely different approach will be presented, one using the concept of a differential annihilator operator. And since that gets into more of your operators and stuff, frankly, I don't see a lot of difference. It says to us, the instructor, take your pick. I've taught it both ways. It seems like to me that students understand the superposition more quickly. They grasp it more quickly than they do the annihilator approach. Now, maybe you'll find it differently. We're only going to do superposition. Okay? So strictly speaking, g of x is equal to k, a constant, is a polynomial function. Okay? Since such a constant function is probably not the first thing that comes to mind when you think of a polynomial function, for emphasis we will continue to use the redundancy of constant functions and polynomial functions. Actually, constant functions are polynomial functions. So the following functions are examples of the types of inputs g of x. Okay, let's go back and see if I can get both of these on the screen at one time. May not be able to. Yeah, here we go. Constant function k, which could be considered a polynomial function. So basically, polynomial functions, exponential functions, sine or cosine functions, or finite sums and products of any of those. Okay? Notice finite there. Okay? So let's say you have a constant function, g of x equal 10. That would be one example of that. A polynomial function, g of x equal x squared minus 5x. That would work. Okay? Now, a sum of a polynomial plus an exponential, that would work. 15x minus 6 plus 8x to the minus x. 8e to the minus x. That would work. A sine or a cosine function, or a sum or a product of those. So that would be a sine 3x minus 5x times cosine 2x. So you see, they don't have to have the same b's here, okay? Multipliers of the x, they don't have to be the same. This is a sum of two different ones, sine beta x and a cosine different beta x, okay? And this is a product of a polynomial function times an exponential function times a sine function, the sum of that with a polynomial function times an exponential function. So my goodness, they can be complicated. Okay? Now, that is, g of x is a linear combination of the functions of any of these types. Polynomial functions, that can be as many as you want to, x to the nth. Okay? Exponential function, e to the alpha x. A p of x times e to the alpha x. A p of x times e to the alpha x times the sine of beta x. A p of x, e to the alpha x cosine beta x. Okay? Anything such as that, any linear combination of functions of any of those types. Notice this has the polynomial function in it, the polynomial and the exponential and the sine or cosine, and the polynomial exponential or cosine, sine or cosine. Okay, and then any linear combination of them, you can have some constant multiplied by one that looks like this, added to or subtracted from a constant value that looks like this or like this or like this, any way you want to put them together. We're in here. Oh, the ends here in the polynomial always have to be non-negative integers. You can't have n being a fraction, a decimal. It has to be a positive integer. It can't be a -1. It could be a -2/3. It couldn't be a 3/5. It couldn't be a 0.7. It couldn't be any of those things. It has to be a positive integer. You're n. Okay? The a's can be anything they want to be. Any constant. Okay? Okay? The alpha and the beta are any real numbers. That's here. That could be a square root of 3, a 0.5, you know, anything. Beta, same thing. Any real numbers. Okay. Goodness, I'm running out of steam here. Sorry, I think I would be able to do 5 more minutes, but boy. Part of this is the anemia, but part of it is also hunger. Because I only had time for eat a few carrots between my first and second class, and 1 bite of a sandwich between my second and third class. Okay, this class. All right. The method, let me use this one, this is better. The method of undetermined coefficient is not applicable to equations of this form. Okay, I mean of form 1, g of x on the right hand side, when g of x is log x, not going to work. E to the x, fine. Log x, not fine. Polynomial, fine. Rational, not fine. Sine or cosine, fine. Tangent, not fine. Sine, fine. Inverse sine, not fine. Okay, inverse cosine, not fine. So it has to be one of these. If it's not one of those, this method isn't going to work. Okay? The set of functions that consist of constants, polynomials, exponentials, sines, and cosines has the remarkable property that derivatives of their sums and products are again sums and products of constants, polynomials, exponentials, sines, and cosines. Because the linear combination of the derivatives must be identical to the g of x, it seems reasonable to assume that the y sub p will have the same general form of g of x. And let's see if we can squeeze in 3 minutes this first one. Okay? I doubt if we'll finish, but we'll get started. Okay? So let's go to our whiteboard. Sorry, today hasn't been as a very full class. Let me move y'all back where you were. You can't see it, but I can. Okay. This is, oh man, where am I? Okay, I hadn't flipped my pages in my book. Example 1. Okay. Y double prime. We're basically only going to get started on this one. Let me get book in my lap because I can't read that far away. Okay. Makes it so much easier to control the pen too. Y double prime plus 4y prime. And we just lost Kara again. Minus 2y is equal to 2x squared minus 3x plus 6. Okay. Now, when you're doing these all the way through, first thing you do is your associated homogeneous one. And that's y double prime plus 4y prime minus 2y is equal to 0. Okay, now we've got 1 minute. This has a solution always of the form y is equal to e to the mx. And that produces your auxiliary equation of m squared plus 4m minus 2 is equal to 0. Okay? Now, first thing I would try, always look to see if it will factor. This one will not. Okay? So next we go to quadratic formula. M is equal to minus b, in this case minus 4, plus or minus the square root of, b squared, which is 16, minus 4 times a, which is 1, times a minus 2. That's your c. Okay? All over 2a, which is just 2, because a is 1. Alright, let's take that another step. That's minus 4 plus or minus the square root of 16, and you got, count your minus signs. 1, 2, that means that's going to be a plus. That will be 8. 16 plus 8 is 24. Divided by 2. Okay? Now, that'll be a minus 4 plus or minus. Are there any perfect squares in 24? Well, I know 4 is in there. It's 4 times 6. 6 isn't a perfect square. There's no perfect squares in there. So that's going to be 4 plus 2 times the square root of 6. Right? Because 4 times 6 is this. 2 squared is 4. Okay? Divided by 2. So this 2 will go into that 2 times and go into that 1 time. So our solutions are m is equal to minus 2 plus root 6, okay, and minus 2 minus root 6. Okay. Now, that means your two characteristic complementary solution, I always get the words wrong, will be y sub c is equal to c1 e to the minus 2 plus 6, that's a minus 2. Yuck, this thing drives me nuts. Okay. Okay, minus 2 plus root 6 x plus c2 e to the minus, get out of there, e to the minus 2 minus root 6 x. Okay, I think I've got my parentheses in the wrong place there. Okay. Okay. No, it was in the right place. It was in the right place. Sorry. couldn't tell that one. That one's in. Okay. That's your characteristic solution, and we're out of time. So we will pick up with step 2 next time. We'll just write down what we've done so far and pick up with step 2, which is where the real work begins. All right. Any questions on anything we've done so far? And like I said, Jemanuel, I'll try to get that letter done now and send it to the records office if that's where I sent it to last time. Okay? Any other questions, issues, concerns, problems? Okay? 2 more things. Number 1, have a great Thanksgiving. I guess you know there are no classes next week. Okay? The college will be open Monday, Tuesday, and Wednesday, though I wouldn't push Wednesday very far. It's quite common on a Wednesday afternoon right before Thanksgiving that the supervisors start letting people go home to start working on their Thanksgiving meals. Okay, so I would not bank on finding anyone you might need Wednesday afternoon. I think even Wednesday morning may be tough because they may be taking personal leave. Okay, that's fine too. If they got it, they can take it. But generally Monday and Tuesday, most places will be open. There may be some people taking the whole week off. But Wednesday, generally all the offices will be open in the morning, but don't bank on them being open too late into the afternoon. So if you got business with the college, get it taken care of. Monday, Tuesday, or Wednesday morning will be safest. Okay? And let's see, anything else? Be careful, because I know you want to get together with family, you want to get together with friends, you want to do, hey, this COVID stuff is getting completely out of control. I mean, hospitals are running out of equipment. They're wearing their people completely out. There aren't enough people to take care of all the people that are coming in sick. It's just getting to be a terrible situation. Okay? And we have no leadership at the top letting us know. UAB is doing a fantastic job for the state of Alabama, but not that many people pay attention to UAB either. So please be careful. That's number 1. You'll have plenty more Thanksgivings. I hope that you can get with family and friends as much as you want to. Try to be careful this time. Really careful. Any questions? All right. We'll see you then the week after Thanksgiving, that Monday morning after Thanksgiving. 1 more week of class, then finals week. So not got much more to go, folks. See you then. Bye-bye. Any last thoughts before I end the meeting for both of us? Okay. Take care. See you Monday after Thanksgiving.